Hello everyone. My name is Hoang Thanh, and I'm a student at the Leipzig University in Germany. I would like to introduce to you a variable neighborhood search for a dynamic orienteering problem. The orienteering problem is derived from a sport that is known as score orienteering, where participants are given a map that looks a bit like this. So on this map, you can see that there are many points spread throughout the map, which are numbered, and each of which have a value assigned to them. And given this map and a time limit, the participants have to run to these so-called checkpoints. And each of these checkpoints rewards the participant a certain number of points. The goal is to collect as many points as possible within the time limit. However, the order with which the checkpoints must be visited, as well as the number, how many must be visited, is not fixed. So it is necessary to plan the route beforehand. It can be easily seen that this is a combinatorial optimization problem, and it also has applications in other areas besides the actual sport. For example, when we want to plan routes for tourists. So tourists only have a limited time per day, and they want to see many interesting sightseeing spots. And there we have to plan a route for the tourists so that they can see many attractive spots within a day. Another application might be when we have to deliver goods to customers. So customers pay more money, some customers pay less money, and we have to decide which customers are served and which customers need to wait until the next day. And here in this work, we particularly considered a dynamic variant of the problem, which means that parts of the problem can change over time. This can also occur in many practical applications, for example, when a traffic jam occurs or when a customer changes his or her order. And it might also be the case that there are daytime-dependent changes. For example, some sightseeing spots might be more attractive in the evening than in the morning. Okay, so after introducing to you this problem, I'd like to describe it in more detail. And then I'm going to present the proposed algorithm that is based on variable neighborhood search. And after that, I'm going to explain how the experiment was prepared to evaluate the proposed algorithm. Then I'm going to present some computational results and finish with some concluding remarks. Okay, well, the problem can be easily described using a graph with nodes and edges. Here, for the sake of simplicity, we restricted ourselves to the case with an undirected connected simple graph. And there, every node has a score and every edge has a length. We're also given a budget as well as a depot node. And the task is to find a path that starts and ends with the depot node that maximizes the total collected score and where the length does not exceed the budget. And as mentioned before, we consider a dynamic case. So we have dynamic changes that occur over a time horizon t. Here, we restricted ourselves to the case where only the nodes change their score. So this case has the property that a valid solution cannot become invalid over time. And it should be noted that here the time horizon t refers to the runtime of an algorithm solving this problem. So while an algorithm is running, it is possible that the problem changes so that it has to adapt to these changes. This is to be distinguished from the time at which a node is reached, as there are some works that use the latter definition for time. And well, for this reason, it is preferable if algorithms are able to work with existing solutions and quickly improve them if changes occur. So it would be good if algorithms could do that instead of just restarting whenever a change occurs. And it's also this reason why we focus on improvement heuristics, which are algorithms that improve a given initial solution. And the improvement heuristic that we propose is based on variable neighborhood search. The basic principle of variable neighborhood search is to repeatedly improve a solution with respect to an objective function by going to a similar solution that is in the neighborhood of P. Here, neighborhood refers to a set of solutions that are considered similar. And this is done repeatedly until an improvement is not possible anymore. And then we change the neighborhood to a different one. And by doing so, we also change the set of solutions considered similar. And this is based on the assumption that a local optimum with respect to one neighborhood does not necessarily have to be a local optimum with respect to another neighborhood. Okay, and so how did we adapt this principle to the orienteering problem? Well, we thought about this problem and we found that the orienteering problem contains two interacting subproblems. The first problem is to select a subset of nodes that have a high total value, and the second problem is to calculate a short path that traverses the selected nodes. And it might happen that we solve the second problem, so we calculate a short path between the nodes, and we find out, oh, it still exceeds the budget. It's still too long. So we have to select another subset of nodes. So the problem one might have to be resolved if the solution of problem two exceeds the budget. And in this sense, one might say that the first problem is a bit similar to the knapsack problem, where we have to select a set of items while taking into account a weight restriction, whereas the second problem is a bit similar to the traveling salesperson problem, where we need to calculate a short path. And the algorithm we propose has been adapted to this problem structure. So what did we do? We now adapted the principle as follows. We now have an objective function that also has an index L, and the neighborhood also has an index. This means that the function and the neighborhood now change depending on the subproblem that the algorithm currently focuses on. Or in other words, the selection of new solutions and the structure of the neighborhood is now determined by the pair f and n. Now, as for the neighborhoods, we considered the following ones. So for the orienteering problem, a solution is a path through nodes. So we considered the add neighborhood, which is the set of paths obtained by inserting a node into the path, and a remove neighborhood, the set of paths obtained by removing a node. As for the functions, we used for this work. These are the difference in length between two solutions, the difference in value, the ratio between the two aforementioned functions, as well as a random value. These functions have been chosen in accordance with the aforementioned subproblems. For example, if we only consider the length between a difference in length between two solutions, it's a bit like focusing on the TSP-like subproblem, where we want to calculate a short path. Or if we only focus on the value, then it's a bit like a focus on the knapsack problem, where we only want to have a high value for the total solution. And so the functions kind of determine the focus on the subproblem. Okay, after showing the neighborhoods and the functions, I would like to give you an outline of the proposed algorithm, which is named VNSDOP. It is an improvement heuristic, which means that it starts with a given initial solution. And the next step is to perform a short initial exploration phase based on this solution. And there we repeatedly add nodes to this path in a random manner and remove them if the solution is invalid. And after this short initial exploration phase, we select two functions randomly from the four aforementioned functions. And then we repeatedly perform search steps with respect to the add neighborhood and the function f1 until the solution cannot be improved. So we add nodes until the path becomes invalid, as it exceeds the budget, or until there are no more nodes left to add. And then we shorten the resulting path using the chained Liefooghe heuristic. This is a commonly used heuristic for traveling salesperson problems. And if the path is still too long, then we repeatedly perform search steps with respect to the remove neighborhood and the function f2 until the path becomes valid again. And if the termination criterion is not satisfied, we go back to step 3. So in essence, the algorithm repeats these 3 steps, 4, 5, and 6. So we repeatedly add nodes with respect to f1 until the solution becomes invalid or until no more nodes can be added. Then we shorten the path with the Liefooghe heuristic, and then we remove nodes until the path becomes valid again. And we designed the algorithm in this way because we aimed at some properties that would allow the algorithm to deal with the dynamic orienteering problem. One is that we have functions, and the functions determine how new solutions are selected, and these functions now change in accordance with the 2 subproblems. And another property is that the proposed algorithm constantly tests a variety of solutions in order to adapt to changes. It does so, for example, by a random selection of functions in each iteration. And by doing so, we want the algorithm to have a degree of variation in each iteration. And we also employ a random function that acts as a perturbation mechanism and strengthens the exploration. Okay, after describing the algorithm, I would like to explain how we prepared the experiments to evaluate the algorithm. To the best of our knowledge, this type of dynamic orienteering problem, where, well, the problem changes over time, has not been considered before, but there exist many algorithms for the static orienteering problem. So we chose two state-of-the-art algorithms for the static problem in order to compare ourselves with them. These are an evolutionary algorithm, as well as a greenly randomized adaptive search procedure with segment removal. And well, since we consider a dynamic problem, we also had to think about how to measure time, as time determines how the changes occur, and it also affects the evaluation that is performed later on. Here in this work, we considered two time measures. One is the number of function evaluations, which means how often the length and the value of a path is calculated. And it could be said that this kind of focuses on the TSP-like subproblem, where, well, every path and every length measurement counts. And the second time measure is the number of subsets, which means the number of subsets of nodes that have been considered so far. And for example, for a given subset of nodes, it is possible to calculate many paths that traverse these nodes, but this only counts as one subset. So it could be said that this kind of focuses on the knapsack-like subproblem. And by choosing the time measures like this, which are also hardware independent, the evaluation focuses on the performance of algorithms with respect to these two subproblems. The next question we asked ourselves is, how does the value of a node change over time? So for this, we did the following. We took the two aforementioned time measures and defined a discrete time horizon from 1 time unit until 1,000,000 time units. And on this time horizon, we equidistantly spread L points in time, and at each of these points, we randomly change the value of a random node. And in this work, we considered, or we set L as the number of points of interest and half of that number. And the reason for this choice is that in the former case, it is possible that every node in the graph changes its value at least once. Okay, as for the test instances, we use two sets of instances with a focus on road networks. The first set is a set of networks based on OpenStreetMap data. Here you can see an example on the left, how it looks like an OpenStreetMap and how the corresponding graph looks on the right. The next set of instances is based on OPLib, which is a benchmark for orienteering problems. And in total, we had 110 instances, which contain 22 static instances, as well as 88 instances for the dynamic orienteering problem. And since we work with improvement heuristics, we also generated initial solutions of varying quality for each instance. Okay, next I would like to present to you some computational results. So we let all three algorithms run on all 110 instances with all initial solutions and 10 repetitions. And the data that we measured has then been used to calculate progress curves. A progress curve is a curve that shows over time how the best solution so far, or what the quality of the best solution so far is. So some people might know this from the traveling salesperson problem. That is a curve that goes down over time, which shows how the best solution found so far becomes shorter over time. And here for the orienteering problem, it is better if the solution has a high value. So high values are desirable here for the progress curves. And the progress curves here were averaged over these 10 runs, and we had a total of 660 progress curve diagrams. One example can be seen here. So yeah, this is just an example. And as mentioned before, it is desirable if the curve has a high value, but you can also see how the dynamic changes affect the performance of the algorithms. So sometimes the red algorithm is better, sometimes it's the blue one that is better. So we also had to think about how to compare algorithms. If one were to just focus on the solution quality at a certain point in time, then, well, doing so would lead to neglecting other points in time where an algorithm might have been better or worse than others. So we found that it was important to take the performance over the entire runtime into account. And for this reason, we chose an aggregate quality measure that is known as the area under curve. Here, a high value means that an algorithm quickly obtains a solution of high quality with respect to the time horizon. And yeah, for all the progress curves we plotted, we calculated the AUC values and averaged them over different sets of instances in order to investigate how the parameters of the instances affect the performance. And by doing so, we obtained a table that looks a bit like this. So here, a value close to 1 means that this algorithm performs best on average on the considered instances. So this table might be a bit difficult to read, so I'm going to give you an example. So this value here means if we only consider the progress curves where the initial solution was a random path, and if we only focus on the time-measured function evaluation, then the evolutionary algorithm had on average an AUC value that was 93.8% of the best AUC value for the considered instances. So this is an example how this table is supposed to be read. And you can see that the EA, for example, outperforms the GRASP algorithm, here abbreviated as GSR. And in bold font, you can see the best values in each category. And it can be seen that the proposed algorithm obtains the highest values. So this indicates that it has consistent high performance over time for different initial solutions and levels of dynamic changes in the score function. We also performed some more experiments to compare these algorithms. However, presenting them here would unfortunately go beyond the scope of this talk. So to summarize, we considered a dynamic orienteering problem where nodes change their value over time. And we proposed an improvement heuristic that is based on variable neighborhood search. The algorithm has been designed to utilize the problem's structure and to constantly test a variety of solutions in order to adapt to changes. And well, we compared this algorithm with 2 other algorithms that are based on state-of-the-art methods, an evolutionary algorithm and a greedy randomized adaptive search procedure. The evaluation we performed focused on the solution quality over the entire runtime. And we used instances from an existing benchmark, as well as instances generated from existing road networks. And the results indicated that the proposed algorithm obtained a high performance over time for different initial solutions and different dynamic changes for node values. I'd also like to mention that the complete code for all algorithms, instances, and evaluations is available on GitHub. And of course, there are some open research questions that we're going to look into in the future. One is we would like to investigate in the future how the dynamic changes affect the algorithm's performance in more detail. And we would like to perform research on how this effect can be quantified. And another question is, well, we only considered the case where nodes change their value over time. But it's also possible that an edge might change its length over time, the graph might change its structure, or the budget might change over time. However, in this case, it might happen that a valid solution becomes invalid over time. So this would also require research on mechanisms to repair invalid solutions. All right, so with this, I'd like to conclude my presentation, and I thank you for your attention.
Thank you. Thank you for your presentation. Now it's question time. If someone have a question, please. No question. Christine, yes, have a question?
Hi, thank you very much for your talk. I might have missed it, so I apologize in advance for that. Can you go back where you described the dynamics of the problem?
Yes, the dynamics of the problem, yes.
So if I understood correctly, you have basically at a certain, well, after certain time steps, you decide randomly if you want to change the value of the node, right?
Yes.
How do you change the value of the node? Is that additive? Is that multiplicative? multiplicative? Is that just a new random value in an interval? So how do you make that change?
Yes, that is an absolute change, and the value that we use is based on the initial value, but then we only do absolute changes in the interval based on the initial value.
So you basically draw a new random value from an interval.
No, it's like we add or we subtract a value.
Okay. Okay. So is that a large magnitude or rather a small magnitude of change? So if you consider the whole range of values.
As for the range, we the interval that can be like the delta that can be added, we set this value to be like half of the initial value of the corresponding node.
Okay.
So yeah, so it is a bit like based on the value that the node has.
Do you plan to look into that as well as a sort of future work where you can think of having different ways, different magnitudes of change, not just
yes. Yes, we
Okay.
definitely intend to look into that, as this is of the point that I mentioned here. There are many ways on how the values can change, and yeah, and this is definitely a point that we're going to keep in mind for the future.
Yeah, I think it's really interesting to see different ways to change the problem, both with respect to frequency and magnitude of change. So yeah, really interesting. Thank you very much.
Okay, yeah, thank you for your question.
And other question? Is it possible to imagine to change the value of other points when you visit a point? It's more realistic, I would say, that when a solution visits a point, then the other value will change only and not during the process.
Yes, so it would be, yes, this is also a different type of dynamic problem that can be considered. So yeah, in this work, we only considered the case where the changes happen, well, during the runtime of an algorithm. And there are works that consider the case that you described, where when when the path arrives at a certain node, that then the value changes. This is also known as a time dynamic problem. And yeah, this problem also has been considered before in the literature.
I've got a question, Sebastian.
Please.
It's more of a comment. Really good talk, and we actually have done some work on different types of dynamics, but more in an engineering context. So we had exactly this type of problems where the constraints change over time, or the decision variables change over time, and so on. And you may want to look at that work as well. For example, you might have a change because of a decision you have taken in the past. So that may change. For example, certain parts of the search space become available or unavailable temporarily. You also might see changes like if you commit to a particular solution, or then you have to maybe, or if you commit to a particular subroute, you maybe have to stick to this subroute for a number of evaluations. I mean, if you go down, let's say, a one-way street, you may not be able to go back. So it's committing to certain things. So I can point you to that. We call these constraints in engineering ephemeral resource constraints, but we also have seen similar dynamic changes, for example, in drug discovery, where the biologists say halfway through the optimization, I'm not happy with the drugs, I want to change 10 of my drugs and replace them with new ones. So in your case, it would mean, for example, you remove some of your nodes and replace them with new nodes located in different parts of the map.
Oh, okay, that is an interesting suggestion. Could you please say the name again of these type of dynamics?
I mean, these constraints are called ephemeral resource constraints. I'm happy to share with you some couple of papers.
Then yeah, I would be glad if you could share with me some papers on that matter. This is a very interesting topic, and yeah, thank you for your comment on this.
Thank you for your comment. So